Hi there. In today's lecture, we're going to be looking at implicit differentiation. So previously, we looked at explicit differentiation. So that is where we have y is equal to some function of x. So we know what is our independent variable, we know what our dependent variable is, and it's quite easy to take the derivative. In this case, with implicit differentiation, the functional form is implied instead of explicitly written. So just by looking at this expression here, x squared plus y squared equals 1, it's not so clear which is the independent variable and which is the dependent variable. Okay, it is implied. So we just assume that y is a function of x. So we can rewrite this as x squared plus y of x. So we write the functional form out, squared is equal to 1. Okay, so here we can see where the function actually is. Okay, and another thing to notice is the function we're interested in is itself inside another function. So here it's inside the function something squared. Okay, so if you remember back to the previous lecture when we looked at the chain rule where we had composition of functions, we see we're going to be needing that quite a bit here. Okay, so normally we suppress this functional notation and just assume that y is a function of x and work with that. Okay, so how do we find the derivative y prime? So the first thing we notice, so just make a quick note, is that if f of x is equal to g of x, then f prime of x is equal to g prime of x. Okay, so that might seem very obvious, however, it will help us quite a bit here to give us our first step at finding the derivative. So what this says is that if we've got some expression, okay, left-hand side equals right-hand side, then if we take the derivative on both sides, the equality is maintained. Okay, it's like multiplying both sides by 2. The equality is maintained. So let's take our original expression, x squared plus y squared is equal to 1, and take the derivative on both sides. So we're going to have d by dx of x squared plus y squared is equal to d by dx of 1. Now we can take the derivative on the left-hand side, keeping in mind that it's not just y squared, it's y as a function of x inside the function something squared. So we need to use the chain rule. But the derivative of x squared, that's standard, very simple, that's going to be 2x. Plus the derivative of y squared, as we said, we need to use the chain rule, so that's going to be 2 times y prime. So we differentiated the outside, so that will be 2 times y, then we differentiated the inside, so that will be y prime. Then, on the other side, the derivative of 1, that's going to be 0. Okay, so notice the right-hand side is 0. On the left-hand side, we've got a couple of 2's there. We can get rid of those by dividing both sides by 2. Then we can take the x over to the other side. So we have y prime is minus x. So y prime is minus x over y. Now, it may seem odd that the derivative is in terms of x and y. Usually, we have that the derivative is in terms of x only. But we will see that this is a common feature with regards to implicit differentiation. Now, this as an answer is perfectly fine, but it's useful to draw a little picture just to see that this does work out. Okay, and the way that we do that is by sketching what we started with. So x squared plus y squared equals 1. That's the equation of a circle. So let's draw a circle here with some radius. Okay, and at some point we have the tangent line with this given gradient. So let's say the tangent line looks something like that. Okay, at this point, xy. Okay, so here we've got two different gradients that we can consider. We can have the gradient m1 of the tangent line and the gradient m2 of the radial line. Okay, so we can calculate these two and we'll see that it is quite interesting. So firstly, m1, the gradient of the tangent line, that is this y prime that we found. On the other hand, m2, the gradient of the radial line, since the line is passing through the origin, there's no y-intercept to worry about. So this is quite easy to work out. It's just going to be y over x. Okay, quite easy to do there. Now, what's surprising is when we take the product, m1 times m2, we get minus x over y times y over x. The x's cancel, the y's cancel, and we're left with minus 1. Now, if you remember back to your analytical geometry, if we have the product of the gradients being minus 1, it means that the lines are perpendicular to each other. So what this means is that the tangent line is perpendicular to the radial line. Okay, and this is true for any point, right? We didn't specify any point in particular, we just took any point on the circle. So the tangent line is always perpendicular to the radial line. And if you remember back to your Euclidean geometry with all the circles, remember that was one of the facts or one of the theorems that you went through. Okay, so you could prove it in a Euclidean way with shapes and lines and so on. You can also prove it using some calculus, okay, which is quite interesting. Okay, so let's have a look at some examples and then we will get into the main use of finding derivatives of inverse functions. Okay, so let's look at some examples. Okay, number 1, x squared plus sine xy is equal to 2. Okay, so it looks a bit complicated because we have the sine of x times y, so we're going to have to use the chain rule because we've got an outside function and an inside function. And also on the inside, we've got a product of two functions. So x, that's a function of x. Y, that's an implied function of x. So we're going to have to use the product rule there. So chain rule on the outside, product rule for the inside. Okay, as with all of the examples, the first step is to take the derivative on both sides. So d by dx of x squared plus sine xy is equal to d by dx of 2. Now we can take the derivative. So the derivative of x squared, that's going to be 2x, plus the derivative of sine, that's going to be cosine, the inside stays the same, times, now we have to take the derivative of the inside. So the derivative of x, that's going to be 1, let's put that down, times y, we leave the second part alone, plus x, and then we take the derivative of y, but that's just y prime. The derivative of 2, that's just going to be 0. Now we want to solve for y prime. Okay, so let's multiply out that bracket so that we can eventually get y prime by itself. So 2x plus y cos xy plus xy prime cos xy is equal to 0. Now, all the terms with y prime, we want to keep those on one side because we want to solve for y prime. And everything else, we can just take over to the other side. Okay, so xy prime cos xy is equal to minus 2x minus y cos xy. Now this might look complicated. We've got a lot of x and y's and cos of x, y's and so on. However, all of the major work has been done already. Okay, we've done the derivative. All we have to do now is solve for y prime, and that is just a bit of algebra. Okay, so the major work is done. Now we can divide both sides by x cos xy, and that will leave y prime by itself, and the right hand side is just going to be the gradient. Okay, so it's a bit messy, but that's what we've got. So y prime will be minus 2x minus y cos xy all over x cos xy. Okay, again, it looks a bit messy and complicated, but once we've done the derivative work, the rest is just some algebra. So taking some terms over to one side, dividing by other terms, that should be quite easy to do. Okay, let's have a look at two more examples, and then the rest will be saved for the tutorial. Okay, example number 2. X squared y squared plus cos x y squared is equal to 3x. Okay, something like this. So fairly similar to what we had before, maybe a little bit more complicated. Okay, but always the same step, same first step, take the derivative on both sides. So we have d by dx, everything on the one side, and then d by dx, everything on the other side. And again, we notice for the first term, we've got an x squared times y squared. That's a function of x times a function of x, so we're going to have to use the product rule. Then y squared, that's a function of x inside a function of x, so y, that's a function, and then we have something squared, that's another function, so chain rule for that one. Similarly, for the cos term, we have an outside function, so chain rule is going to apply there. Then on the inside, we've got the product of two functions, so we're going to have to use the product rule there. Okay, so you should always think to yourself, what's going to happen in the next step? What do I need to look out for? Okay, so first bit, x squared, y squared. Let's take the derivative. We take the derivative of the first term, so that's going to be 2x, leave the second alone, plus, we leave the first, take the derivative of the second, remember to use the chain rule. So that will be 2y, y prime, plus, we take the derivative of the outside function, so that's going to be minus sign, so let's put a minus instead of a plus, sine xy squared, times, now we take the derivative of the inside part, noting that we need to use the product rule and chain rule where necessary. So the derivative of x, that's just going to be 1, so we can just write y squared, plus, we leave the x alone, the derivative of y squared, we need to use the chain rule, so that's times 2y, y prime. Okay, so a little bit more difficult, but if you just keep track of what you need to do, it's not so bad. Then the derivative of 3x, that's just going to be 3. Okay, so that is all the derivative done. What we need to do now is solve for y prime, and that is just a bit of algebra. So where are these y primes? We've got one over here, we've got one over here. We would like to keep that on one side, take everything else over to the other side, and then we can solve for y prime. Okay, so 2xy squared plus y prime, let's put that out in front there. Then we have 2x squared y left over. Okay, minus y squared sine xy squared. Then plus, we've got that other y prime, let's put it out in front. Then we have 2xy sine x squared, xy squared. Okay, and then this plus, that should be a minus because of the sine. Okay, so that part's done, and then this is still equal to 3. Okay, so again, let's see where those y primes are. We've got the y prime there, we've got the y prime there. We would like those to be on the one side, and then everything else, let's put that in green. So that bit and that bit, we're going to take that over to the other side. Okay, so we have y prime, and then let's gather those other terms. So 2x squared y minus 2xy sine xy squared. That's for the one side. For the other side, we're going to have the 3 minus 2xy squared plus y squared sine xy squared. Okay, almost done. Now we just need to divide through by that term attached to the y prime, and then we're done. So finally, y prime will be everything on that right hand side. So 3 minus 2xy squared plus y squared sine xy squared all over 2x squared y minus 2xy sine xy squared. And again, this looks very messy and complicated, but if we look back here to when we did the derivatives, so this line over here, after that point, it's just a bit of shuffling terms around and dividing by other terms. Okay, so where that star line is, that's it for the derivatives. Everything else is just some algebra. Okay, so you may notice that you could simplify the expression. So here you can't really simplify that much, so that's fine, but that is not necessary. Okay, so once you find the derivative, you can stop there. You don't need to simplify any further. Okay, so I think that's enough examples for this. Maybe one more. Okay, we can go through, and then we'll look at the main part of finding derivatives of inverse functions. Okay, so last example. Let's say we have e to the y times x is equal to cos xy. Okay, something like this. Okay, again, a bit more complicated than before. We've got an exponential now. We've had a cos term before, so that's not so bad. But as always, we start by taking the derivative on both sides. So, d by dx of e to the y times x, and d by dx of cos xy. Okay, so the first part, product of two functions. Again, we need to use the chain rule for the first bit, product rule because we've got two of them being multiplied. So, derivative of the first function, that's just e to the y, but remember chain rule, so times y prime. Plus, we leave the first function alone, take the derivative of the second, but the derivative of x is just 1, so we can leave it like that. Then, the derivative of cos, that's going to be minus sine, so minus sine xy, times the derivative of the inside. The derivative of x is just 1, so we're left with the y, plus x, and the derivative of y, that's y prime. Okay, so let's see where the y primes are. We've got one over there, we've got one over there. So we just need to expand that right-hand side a bit, collect the y prime terms, and then solve for that. Okay, so let's expand that right-hand side. So we're going to have y prime, let's put that out in front, e to the y times x plus e to the y is equal to minus y sine xy minus x y prime sine x y. Okay, so again, where's the y primes? We've got over there and over there. So we need to take that over to the other side. Then this e to the y, we need to take over to the opposite side. Okay, so we have y prime, then e to the y times x. Then the minus will become a plus when we take that over. So plus x sine xy. So that takes care of that. And then on the other side, we have minus y sine xy. Then the plus, that will become a minus, so minus e to the y. Then we can divide through, and we're done. So y prime will be minus y sine xy minus e to the y over e to the y times x plus x sine xy. And again, we can just leave our answer like this. Here we can't really simplify any further, but if you could simplify, you may do that if you want to, but it isn't required. Okay, so let's have a look at the main part that we wanted to get into, finding the derivative of inverse functions. So finding the derivative of inverse functions. Okay, so we will go through the method by looking at an example. So let's say we have y is equal to sine inverse of x. Okay, sometimes this is written as arcsine. Okay, so that's just some notation. Okay, it means the same thing. So how do we find the derivative? Well, we know how to work with the trig function sine. That's easy to do. But sine inverse, that's more difficult. So what we can do is take the sine on both sides. Okay, similar to how you can just square both sides or multiply both sides by 2. We can apply the sine function on both sides. And note that the sine and the sine inverse, they will cancel. Okay, so simplifying what we've got. So we can have the sine of y is the sine of sine inverse of x. Okay, but like I said, the function and its inverse, they're going to cancel, and we're just left with x. Now, if you look at that for a little bit, you'll see that we now have an implicit equation. So y, that was a function of x, it is now inside another function. Okay, so we need to use implicit differentiation in order to find y prime. So let's do that. D by dx on both sides. And let's just go through. So the derivative of sine, that's going to be cosine. And then the derivative of y, because of chain rule, we get y prime. Derivative of x, that's just going to be 1. So we have y prime is 1 over cos of y. Now, if this was just simply implicit differentiation, we could stop here, because we know that with implicit differentiation, the right-hand side is usually a function of x and y. Okay, we've got x terms and we've got y terms. We've seen that before. But here, when we're taking the derivative of this inverse function, we can go one step further and write it as an explicit function of x. How do we do that? Well, we use this relationship that we've got here. We know that sine of y is equal to x. Here we've got cos of y. They're different, but we know the relationship between the two. We know that sine squared y plus cos squared y is equal to 1. doesn't matter what y is, it's still equal to 1. So let's solve for cos of y. So cos squared y is going to be 1 minus sine squared y. But sine of y, that's just x. So we can substitute that. So cos squared y is going to be 1 minus x squared. You can take the square root. So we get cos of y is the square root of 1 minus x squared. Notice how we leaving out the minus square root part. That will be the homework question, is to explain why we take the positive square root to get our answer and not the negative. Okay, so think about how this function looks like and why the gradient, or why y prime looks like that. Okay, so y prime will be 1 over the square root of 1 minus x squared. Okay, and notice that this will always be positive because the square roots of something will be positive. Okay, so that's a little hint as to why we take this positive square root. So do a little sketch of sine, do a little sketch of sine inverse, and see how does the gradient change along the function, and then you'll see why we need to take this positive root. Okay, so that's just a little exercise that you can do for homework. Okay, for the next example, we're going to have y is equal to the natural log of x, okay, which we defined previously as the inverse of the exponential. Much like how sine and arcsine, they're inverses, the exponential and the natural log, those are also inverses. So we're going to follow the same sort of procedure as before. We apply the inverse of the inverse on both sides. In this case, it will be exponentiation. So e to the y is e to the natural log of x, but those are inverses, so we just get x. Now we get an implicit equation. Okay, the y is in the function there, so it's implicit. We can take the derivative on both sides. D by dx of e to the y is equal to d by dx of x. Okay, so let's follow through with that. The derivative of this, we've done that in a previous example. That's going to be e to the y prime. The derivative of x, that's going to be 1. So y prime is 1 over e to the y. Again, if this was just a standard implicit differentiation question, we could leave it like this. However, we can simplify this, because if we look back here, we know that e to the y is equal to x. So here we've got 1 over e to the y, so that's just going to be 1 over x. So we see that the derivative of the natural log is 1 over x. Okay, so that's quite interesting for now, but we will see that both of these examples, the one with sine inverse as well as the one with the natural log, will show up much later in the semester when we look at antiderivatives and integrals. Okay, so you don't have to worry about them for now, but just make a note that these examples here will show up later. Okay, so please don't forget them. Okay, let's put some homework problems down. Okay, so find y prime. And we've got a few here to go through. Okay, so remember that these homework problems will be on top of the tutorial questions. Okay, so it's just some extra work to go through. Most of the times it will be a little bit more difficult than the tutorial work, and that is just to help you prepare for the tests. Okay, so rather prepare on something a bit more difficult just to give you that extra confidence. Okay, for the first one, we're going to have y is cos inverse. So very similar to the sine inverse. please make note of the sign. So before we chose the positive one, here it might be something else. Okay, so that will be up to you to figure out. Okay, y equals tan inverse. Again, we will see that later on when we are doing antiderivatives and integration. Okay, so please just keep that in mind. Number 3, y is equal to sine hyperbolic inverse. Okay, that might sound a bit odd, but I'll write out the definition for sine hyperbolic, and that should help you with these problems. Okay, and y is equal to cos hyperbolic inverse. Okay, so maybe you haven't seen these before, but I'll just put the definitions down. Sine hyperbolic of x, this is equal to e to the x minus e to the minus x over 2. And cos hyperbolic of x, that's e to the x plus e to the minus x over 2. Okay, so you'll see quite a bit more of these next year in complex analysis, so that's at the end of next year. But for now, you can think of these as extra functions. So we have sine and cosine. We know how they work. Sine hyperbolic and cos hyperbolic are similar. They have similar properties, but a bit different. So we say sine hyperbolic instead of sine. Okay, we'll see that they are more closely related to the trig functions, but again, that will only be next year. Okay, for now, if you want to know where these come from, sine hyperbolic is the odd part of e to the x. Okay, so you can just Google this in your own time. And cos hyperbolic, we say that is the even part of e to the x. Okay, so in general, given some function f, we can write it as an odd part plus an even part, and these two are those specific parts for e to the x. Okay, so you won't be tested on that. You can look that up in your own time if you're interested. Okay, or you can email me or see me in my office if that interests you. Okay, so that will be it for today. If you have any questions on this work or previous work or future work, please don't hesitate to email me. My information is available on the course page, or you can come to my office if I'm available there. Okay, if your question is a bit longer than maybe 5 minutes or so, then please can you book for a meeting? Okay, then I can give you some nice extended allocated time. Okay, but if it's a quick question, please just stop by and I can help you out. Okay, I will see you next time.